When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. That is 6.1 Chatelier principle, and we're going to use that to answer 6.2. Hydrogen gas is prepared by the reaction of methane and steam, as shown in the following balance equation. We can clearly see that we have methane, H2O, to form the hydrogen gas and carbon monoxide. Okay, and then the question is saying 6.2.1, how will the following changes affect the yield of hydrogen gas? Adding more methane. So in our reaction, you can clearly see that CH4 is one of the reactants. So if you increase the amount of CH4, the forward reaction will be favored so that CH4 is used up. The system reinstates a new equilibrium by favoring the reaction that opposes the change. So 6.2.1, adding more CH4, more methane, would increase the yield of H2. So it increases the yield of hydrogen gas. It increases the yield of hydrogen gas. Why is that so? Per Le Chatelier's principle, when there's a disturbance in a closed system, the system reinstates a new equilibrium by favoring the reaction that opposes the change. We have the amount of CH4 increasing. So the system will favor the forward reaction so that CH4 can be used up. And as a consequence of that, the amount of hydrogen gas produced would increase. And then 6.2.2, a decrease in the volume of the container. So this is what we need to understand. A decrease in the volume means an increase in the pressure. Right. So there's an increase in the pressure in our system. How will the system reinstate the new equilibrium? It wants to decrease this pressure. And how does it achieve that? How does the system decrease pressure? It favors the reaction that leads to less number of moles of gas. Okay, but if you take a look at our reaction, we can see that we have methane as a gas, H2O as a gas, carbon monoxide as a gas, and hydrogen gas as a gas. So we need to take a look at the left hand side and at the right hand side, the products and the reactants. In the products, we have 4 moles of gas, right? 3 from hydrogen gas and 1 from carbon monoxide. And then on the reactants, we have 2 moles of gas, right? 1 from methane and 1 from H2O. So it means that if the volume has been decreased and the pressure has went up and we want to decrease the number of moles of gas, then we need to favor reverse reaction. We need to favor reverse reaction because the reactants have less number of moles of gas compared to the products. So in this case, the yield of hydrogen gas would decrease. So we have decrease in the yield of hydrogen gas. And why is that so? For the reasons I just gave, right? We are decreasing the volume, the pressure increases. The system wants to reinstate an equilibrium by favoring a reaction that opposes the change. Since we have increased the pressure, the system wants to decrease the pressure. So reverse reaction will be favored because it leads to less number of moles of gas, hence less pressure. So that is 6.2.2 right there. Okay, let's take a look at 6.3. The sketch graph below shows the changes in the number of moles of methane, steam, and carbon monoxide as the reaction proceeds for the preparation of hydrogen gas in a 2 decimeter cube container. Okay, 6.3, write down the reason why there is no change in the number of moles of each of the gases between T1 and T2. Okay, we can see that the number of moles of all those gases between T1 and T2 remains the same. There is no change. Why is that? That is what we need to explain. The reaction has reached chemical equilibrium. The rate of forward reaction is equals to the rate of reverse reaction. So here we just reached chemical equilibrium. That is why we see no change in the number of moles of the gases. Okay, 6.3. Let's take a look at 6.4. 6.4 says, use the information on the graph and calculate the equilibrium constant Kc for this reaction at temperature T. Okay, there we go. So that table, I think that table takes away from chemistry, because most people can sketch that table, the fill in some values, but they don't really understand what is going on. You can actually answer these questions in the absence of tables, right? But most people use a table. So let's just go ahead and do that also. What do we start with? Okay, let's have our methane gas, CH4, and then H2O, carbon monoxide, and then the balancing coefficient of hydrogen gas is 3. And then this is the initial number of moles. This is the change, number of moles at equilibrium, and the concentration. So let's take a look at our graph. We can see that initially at T is equals to 0, we start with 1.4 number of moles of methane. So this is 1.4. And then that of H2O is 1.2. So we have 1.2. Carbon monoxide starts at 0, same as hydrogen gas. Okay. And then take a look at this at T2 or T1, when we have reached our equilibrium. We find that the number of moles of carbon monoxide is 0.6, the number of moles of carbon monoxide at equilibrium. So we have 0.6. So clearly, the forward reaction was favored, right? We have more products than we had initially. So it means that here there was an increase of 0.6, right? Meaning that for H2O, there was a decrease of 0.6 as the balancing coefficient is 1:1. If the balancing coefficient was, let's say, maybe 2:1, and then carbon monoxide is 1 and H2O is 2, then we would have minus 0.6 multiplied by 2. But here it is just 1. And then minus 0.6 also, because it goes down. And here we have plus 0.6 multiplied by 3. 0.6 multiplied by 3, right? We are multiplying by 3 because of the balancing coefficient, right? So this is 1.8. So 1.4 minus 0.6, that is 0.8, and then 1.2 minus 0.6, that is 0.6, and then 0 plus 0.6, 0.6, 0 plus 1.8, that is 1.8. So we have the number of moles at equilibrium. We need to find the concentration by dividing with 2 decimeter cube the volume of the container. If we do that, 0.8 divided by 2, 0.4. 0.6 divided by 2, 0.3. 0.6 divided by 2, once more, 0.3. 1.8 divided by 2, that is 0.9. We have the concentrations at equilibrium. We can go ahead and find Kc by saying that Kc is equals to the products divided by the reactants. Carbon monoxide, hydrogen gas to the power 3. The power is coming from the balancing coefficient. And then CH4 multiplied by the concentration of H2O. So there we go. The concentration of carbon monoxide is 0.3. That of hydrogen gas is 0.9. And we take that to the power 3. Everything divided by methane. 0.4 multiplied by water, which is 0.3. So we put that in our calculators. Let me just do that real quick. 0.3 multiplied by 0.9 to the power 3 divided by 0.4 multiplied by 0.3. And then I get 1.82. So 1.82. Right, that's it. We don't have an ISI unit for Kc. So there we go. That is the Kc. That is the equilibrium constant for this reaction. That is 6.4. So tell me, here's a question for you. 6.5. The temperature T is decreased. The temperature T is decreased. How will this change affect the Kc value for the above reaction? Write only increase, decrease, or remain the same. The temperature T is decreased. How will this change affect the Kc value? Let me know in the comments what you think the answer to this question is and why. Here we go.